Okay, so basically we're going 3D today. Not much different than when we did 3D particles and stuff, except now we have that moment thing to worry about. So recall, and again we'll go with the engineering baked potato here, there's going to be some rigid body now. Now this rigid body is more than a point, so there's things that basically, there's forces that are not concurrent. And we may even have concentrated couples on it. Again, think about if you're looking at a structure, there might be a beam sticking out with some twist being applied to it. So in terms of what we're seeing there, we might see something there that has concentrated twist or a couple there. And what we found then is what we went through all of this 3D stuff was taking these forces and walking out the door and going to a point, taking these forces, moving them out of their line of action, what created couple, and then we can bring this free couple along, take it to this point O there, and what we find is that we can create a resultant couple and a resultant force. Now the key thing is when we go there, what we're going to do is set those two equal to 0. Nothing fancy. Now when we look at our equilibrium equations, we can express this resultant force as this x, y, and z components. And then the moment as an mz, or a rotation about the x-axis, an my, rotation about the y-axis, and mz, rotation about the z-axis. So the key thing now is we have six scalar equations, because in order to make these equal to 0, which I didn't put up there, each one of these little pieces has to go to 0. Remember, to make a vector 0, the x piece has to equal to 0, the y piece has to go 0, and the z piece has to go to 0. And again, I'll repeat it, if you don't draw a free body diagram, you will lose points. So when we're doing an equilibrium problem, you don't have a free body diagram, I have no idea where your equations came from. So what we'll find, I won't repeat them, but it's basically those same steps. Pick an outline, again, an outline. So we're not looking at what's going on inside. Remember we talked about that when we looked at that piece the other day there with a hinge in the middle. Where's the forces of that hinge? Well, if that's part of the free body diagram, then it's internal to that. We don't show those forces until we pull it apart at that hinge. Okay? So stuff, we're going to be doing trusses and stuff like that. So there's going to be internal forces in those truss members and stuff. We don't care about those because, again, when we talked about setting up our rigid body, it was what was going on externally. So what we're going to be interested then is drawing that external boundary, putting all the forces on it, putting dimensions on it, putting a Cartesian system on it, and that sort of thing. So it's the same steps that we've done before. Now in terms of displaying it, we might want to just do it as a three-dimensional drawing, like we do with the tower problems and that sort of thing. So that's going to be our typical one. Another possibility, especially for those of you that got big into CAD/CAM type stuff, again, project. This is why I'm an engineer, not an English major. Orthogonal projections. So some of you might be more comfortable with that if you've been doing computer work and that sort of thing, but it's basically laying out So you might take your object, and what you do is just simply project it onto the planes. And then you can do things like express your forces there. You take a look at them in terms of how they're acting. So if you're a computer geek and you like to do that, basically it's just taking that object in three-dimensional space there, projecting it onto an XZ axis or a plane, an XY plane, and a YZ plane, and then just kind of manipulating the forces there, getting an idea of how the angles of the forces and that sort of thing. Generally, we'll do this, the three-dimensional. It's a lot easier. Okay, we'll go to our handout. Let's see if I can wake up my computer here. And what we're going to start off with is, again, once we talk about creating this free body diagram, we're going to be pulling it away from things, other bodies, and generally some sort of supports. And we need to think about those support forces in terms of how we're taking them out and what's replacing them. So we take the supports, we're going to remove them, we're going to replace them with the forces. And again, think about the translations and or rotations that are being resisted. If there's something that's saying, I'm not going to be able to go through you, well, then that support is basically going to be providing a force in that direction. Okay, wake up. There we go. You know who I am. Okay, so again, what we're going to do is talk about some of the very similar things there. We may have a plate or something that's being held by a cord. Well, again, the nice thing about a cord, we know its intention, and we know it has to act along its line of action there. But again, what we need to think about is how many unknowns are going to be provided there. In this particular case, it'll just be the one, because we can establish the direction generally. We usually have either a set of angles or a couple of points out there. We can go through that process of creating the unit vector, expressing the force along that direction there, and then solving for the x, y, and z scalar components. Now, another possibility here, too, is a spherical roller here. And basically, it's that or a stick basically on a smooth surface there. And again, think about what's happening. The surface is saying, I'm not going to allow you to go through me. But if you want to scoot along me, not a problem. I'll go ahead and do that. So we're going to have a normal force there, but again, it's perpendicular to the surface, not to the rod. Notice the rod's at an angle there, but the force that the surface is providing that rod, when we take that surface away, is going to be perpendicular to that. I had a few more things hiding there. I don't know why they're all showing up. The other thing is a roller on a friction surface there, or on a guide like a railroad rail or something like that. Again, the surface is saying, I'm not going to allow you to go through me, but since it's now on a rail, or if there's friction, if I try to scoot that thing perpendicular to the way the wheel wants to go, it's going to say, no, I'm going to provide some sort of a force there saying you're not going to go that direction there. So we'll have a force there that's perpendicular to the surface, and then a force then that's perpendicular to the rail or to the wheel axis. So it'll be actually along the wheel axis there. And again, unknowns, we go to 2 now. We've got those 2 components. We don't know how much each of them provide. Finally, ball and socket. Ball and socket's going to basically allow me to rotate, but I'm not going to be able to push through it. I'm not going to be able to go this way, that way, and that sort of thing. So it's going to provide me 3 unknowns. And same thing basically with the next one there, which is just basically a rod on a friction surface. So the friction is going to keep us from going any particular direction there too. So it's going to provide us the same sort of support system there. And again, we'll break these up. We want the x and y components to be perpendicular to each other because, again, we want to feed them into a scalar equation and solve a scalar equation, not a vector equation. Now we get into some weird ones here. These are simple type hinges, basically, that prevent us from going through the surface there and keep us from going along the surface there. Usually some sort of bolted down there. That cylinder thing might be bolted down there. Occasionally, now your author shows that there's some possible moment there too. We rarely use that. It's just in a case, say for example, if you see a piece that's hanging out there and there's a hinge is holding it, that has some slight moment capacity, but I don't know why your author shows it. Almost everybody else doesn't include it because it's generally so small. Especially if you think of that rod going out for any sort of length, there's really not enough moment capacity there. Again, you got to create a couple to resist a moment at the end there, and there just really isn't a whole lot of room there to create that. So generally what you'll see in your homework problems, this is what you're going to see. That's why I wanted to bring that out. So it says, though, that in terms of the length of that axis or that pipe there isn't anything resisting that. So it could slide along there freely if it's a bearing or just a hinge. The next one is the thrust-bearing ones, which basically have something in it like a little notch or something like that, then that will keep it from moving the axis. Again, when you think about a multi-pieced hinge there, if you try to move that, basically those pieces are going to get in the way there and keep you from going that way. So you have the 3 unknowns. Getting things going there. So we'll end up having 3 unknowns there. And then a couple of unique ones. We have the universal joint there, which again provides me those 3 forces when I remove that piece there. But it also provides some couple. And again, that's like a drivetrain on a car and that sort of thing. We're providing some sort of fixed couple there and that sort of thing. So we are going to have that potentially as an unknown. So we'll end up having 4 unknowns there. And then there's finally the built-in case there where it's basically stuck into the wall, providing any sort of, trying to get it to go any direction there. You're going to have the 3 forces there substituting there. But any sort of rotation, it's not going to be able to twist this way, go up and down this way, or be able to go this way. So that'll use up basically all of our equations. We have 6 equations. So when we get to a problem like this, basically, we better hope that the rest of the forces are known, or if we don't know them and it's connected to something else, then we need to go solve those, because by the time we get down to this particular point, we've got 6 unknowns there. We're going to have to start plugging through it. So that's an idea. Again, what we're doing in 3 dimensions is just simply removing these supports, and what we're going to do is substitute these forces, and they're going to come with their sets of unknowns then. Let's see. Okay, next part we'll talk about is stability. We don't talk about this too much in statics, but it's a good idea just to get an understanding. Now what I'm talking about is basically what I'm going to be doing is providing you or going through sets of forces here and explaining how they work. So when you start thinking about structures, you want to think about, okay, is my support cases going to be able to provide resistance against all these potential motions it might have. Now, when we get into some problems, we'll find that it doesn't necessarily mean that everything has to be statically determinate to solve for pieces. We saw that before. So we can start solving for some things. But again, as engineers, you need to think about these particular things in terms of stability to make sure that we're actually keeping the thing where we want it to. So first of all, we'll have some sort of a support maybe at C in the y direction there, maybe a roller or something like that. And basically, the only thing it's going to do is restrain our y translation. If we try to get this guy to go up and down, it's going to say, no, I've got some sort of a capability of force here. If I'm trying to push it down, it'll push back. Now, it didn't say anything about rotation. I can rotate this thing any way I want. But it's basically going to be fixed there in terms of the y rotation. Now, if I add the next piece, B, well, it's in the same direction there. So in terms of restraining y translation, it's redundant. It's doing the same thing. We might want redundancy, especially if we're civil engineers. But the other thing, too, is now that I've got two forces that are out of line, that are out of their lines of action there, I have the ability to create a couple to resist any sort of rotation. So if I try to twist this thing in this direction there, one of these forces can go this way, one of these forces can go that way, and resist my rotation. So in terms of support, I like that in terms of having two of them out, even though it's redundant in the y direction there, it gives me now this extra capability in terms of rotation, resisting that rotation. Next piece is just another one in the y direction there, but it does the same thing. It does the y translation in terms of that, but now it's out of line in the x direction there, which then restrains rotation about the z-axis there. So if I try to rotate this thing about the z-axis, these support forces can change signs. We found we can do that, and create a couple that says, I'm not going to allow you to rotate. Next. Okay, a z1 basically doesn't do anything more than restrain me in the z direction. So if I try to push it in the z direction, if I've got some sort of support there at A in that z direction, it'll say no. It doesn't do anything couple-wise in terms of that, because it can't create those forces are perpendicular to each other. But then the next one will. If we put a BZ in, then again, what we have is the ability now to resist the rotation about that y-axis. So again, it's redundant in terms of the z translation. But now I've restrained all three of my rotations. And we go finally to the last piece there, the x direction there, which restrains my x translation. So again, when I'm thinking about setting up a support for something like that, I need to think about these six possibilities, basically. I need to want to make sure that they are going to zero, either because they're equal to zero, or I've got a set of forces that can force them to zero. Sir?
What isn't the force Cy affect the rotation?
By itself, it doesn't do anything. When we started off there, it was just, these guys didn't exist, right? So it's just saying, I'm going to keep you from going this way, but if I put some force over here on E and these don't exist, it's going to rotate around C without any problem. And where I'm going with this is, again, is that you generally want to set up your two sets of forces along there to keep those rotations. You want to be able to create those couples then to resist any sort of moment that's going on. Convinced? Okay, and we'll also talk about special categories of equilibrium. And again, the reason why we go there is then we're reducing our number of equilibrium equations that we can solve for. So, or we're reducing our number of equilibrium equations. We have then reduced number of unknowns that we can solve for. So in our, say for example, truss situation, we're going to have a lot of three-dimensional trusses. But basically, all of the members are connected to a pin or a point or something like that. What we're going to find then is that we have a set of concurrent forces. And the forces that are available for us there is going to be just simply the x, the y, and the z. There's no moment to be able to take care of, because if I take a moment at that pin, none of those forces have moment arm and won't contribute to any sort of twist. So it's already in equilibrium in that sense. But again, the key thing is that when we run into a situation like that with a set of concurrent forces, then we only have ability to solve for three unknowns. Next one's a rather unique one to 3D is if they're concurrent on a line. So like a drive shaft, and you've got a set of brackets that are tied to it and that sort of thing. Well, what we'll find is that we can resist Fx, Fy, and Fz. We can also resist, we can create couples because those will be out of line there along the y direction and along the z direction, but we don't have anything resisting that x direction, which is kind of good on a car because we actually want it to rotate. But again, if we end up with a set of forces that are all going to a single line, then basically we're going to find ourselves with a situation where we're going to only be able to solve for 5 unknowns. Parallel. This one's probably one of the more restrictive ones there. Of course, if they're parallel, z and y are already satisfied. There's no forces acting in those directions there, so they're not going anywhere. We can only solve for forces in the x direction. And then in terms of moment, we can only solve for moments that are perpendicular to those forces or the y or z. Any sort of moment about any moment about the x-axis is not going to help us. And then finally, our last case there, we have all 3 of them, or all 6 of them available, 3 forces and 3 moments. Okay, and one last thing here. I don't think you have this in your thing there, but go ahead and it's static determinacy. It's basically the same thing we talked about in 2 dimensions there. Statically determinate means basically the unknown forces and the number of independent equilibrium equations are equal. So if we have the situation, say for example, the forces on the drive shaft, then we have 5 unknown forces and we have 5 equations. We can go ahead and solve for everything on that particular thing. Statically indeterminate basically means that we can't solve for all of the forces. So that means we've got more unknown forces than we have equations available. And we might see that a lot of times in certain situations depending on our free body diagram choice. Again, that doesn't necessarily mean I can't solve for something though. Again, we saw that in the 2-dimensional case there, where a set of forces basically, even though there's more forces available, we can set up a relationship between some of them, and with the moment equation, possibly solve for some of them too. And then partial constraints, again, goes back to our stability issue there. The number of support forces is less than the number of independent equations there. And that was kind of what we saw in our stability situation there, that if I provide a shorter number or provide less number of those support forces there, then I may have a stability issue if there is a force acting in one of those directions that I didn't provide any support for. Say, for example, the very last one, the x direction. If there's no x force and there's no x support, I can still solve for things. But the instant I put an x force on it, then it's not going to be a stable structure. Okay, so I think that's the end of the show. Okay, so instead of putting up a overhead, I'm going to just do it here from the computer since I've already got it going. But basically what we're going to do is now start solving for some problems. And just to give you a hint, when we start solving for problems like we did in 2D, our workhorse is going to be that moment equation. What we want to look for is places where there's a lot of forces going to a point, concurrent forces. That's a good place to take a moment because that eliminates a lot of those unknowns there. So just to kind of get a description of what we got here is we got a piece of plywood here. It's a 4 foot by 8 foot. And it was originally perpendicular, but we've leaned it now over a little bit by 60 degrees there. It's leaning against a pipe there, a smooth pipe. How many forces on a smooth pipe? One, okay. And then we've got these little nails basically on the ground there that are going to keep it from sliding out on us and that sort of thing. Everybody got it now? You've got, well, I guess you already got the handout. So our big effort, again, is going to be drawing a free body diagram and then figuring out what those forces are as we start substituting the support forces. I'm going to have to deal with my drawing capabilities here. I'm going to draw it. That's kind of an ugly looking side there. I'll straighten that out. Okay, so that's our plywood. Now we need to start thinking about forces here. We've got that point C that we talked about, the pipe. So it's one force, and what direction will it be in?
Perpendicular to the pipe.
Perpendicular to the pipe. Since the pipe is in the y direction there, then it'll be acting in that z direction, right? That, you guys convinced with that? Okay, let's think about, we got AY here. What's that? You don't get this?
No, what is that? Oh, because
That's the pipe. It's leaning against that pipe, yeah. It's a smooth pipe, so there's no friction there, so I'm allowed to slide up and down it and everything. So it's going to provide me support force in that z direction. So I'm going to remove that support and substitute in the force it's acting. Now let's talk about A. What is it? Oh, question?
does that need vector notation? Or
Is that what?
does that need vector notation, or can you just leave it as CZ?
I can leave it as CZ, yeah. Yeah, I mean, you can make it a vector if you want, you're comfortable, but we know it's the z direction. There's no y or x component. So I won't ding you on things like that if you're specific on that. Let's think about A.
Another perpendicular force.
Okay, perpendicular to.
It's restricted in everything but rotation, basically. It's like a pin, but it's three-way.
Okay, so it's going to keep me from going through the ground, right? So I'm going to have a force, and I want to try to keep it in components so I can develop my equations there. So there's going to be an AY component. Is it going to allow me to slide in the z direction there? No. So I'm going to have a force there. What about x?
Well, it kind of will, but
Yeah, it's a good point. Yeah, we haven't really talked about friction. Yeah, there's probably some friction there. It's negligible right now. And well, we'll talk about that in just a second here when we get all the forces on here. Same thing at BY. Are we comfortable with that? It's going to do the same set of forces.
Yep.
So there's going to be a y component and a z component. Okay, is that all the forces? The plywood, yeah. Where's that going to be? I know, we're jumping ahead to chapter 5 there. It's going to be in the center. So that center of the plywood is where we're going to put it. And as a matter of fact, didn't he say that? No, he didn't. we can assume it's going to be at the center there. So we've got the 40 pounds acting at the center of that. And it's going to be in the z direction. Oh, you're right, negative y. Okay, any other forces? Okay. Now let's go back to we were talking about the x component. In terms of the loads that are known, that are acting on this system, are any of them acting in the x direction? No. No, okay. So we don't necessarily need to worry about it. It's going to be an unstable situation here because if there is a significant x load, the friction probably is not going to be sufficient to carry it and stuff. But in this particular case, we've got a situation where we've got less than enough support in terms of stability, but my load basically is only in that direction there. There's nothing going on in the x direction, so I don't need to necessarily worry about that. Okay, so the next piece and the much harder step is then now I've got to start putting some dimensions here. Actually, this isn't the hard step. It'll be what we do with those dimensions. Okay, so I got 2 feet there, 5 feet there, 1 foot there. I know it's a standard 4x8 piece of plywood there, but it's also rotated by 60 degrees from the horizontal. Okay, and I think that's the main thrust we have in terms of all of those pieces. Now, as I said, the key thing with our 3-dimension is just like the 2-dimension. All we want to do is find some places where we've got concurrent forces and start using moment equations. So I could take a moment equation here, but that'll eliminate the one known I have. I could do one here, but then I'll end up with 4 unknowns there. So generally, I want to take it at one of these 2 places. So we'll take it at A. Now, moment equations in 3-dimension, what we're going to have to do is our position vectors, right? We could do perpendicular distances and stuff like that, but it's generally going to be a lot easier if I can figure out these directions in terms of how to get there. So if I consider this at A, we'll just consider our various position vectors, A, B. So I'm here, and I want to go and look at the forces there at B. My x component will be 5 feet. Y and z will both be 0. So it's just straight down the x-axis there, pretty straightforward. And that's going to be one of my easier ones. I need to go AW. I need to go to my weight there, my 40-pound weight there. So when I think about getting over to that, it's going to be 2 over in the x direction. What about y? Almost. You're a little shorter than that. Don't forget about that part. 2 sine 60. Good. And then the z component will be the same thing we have to worry about. It'll be 2 cosine 60. And actually, it'll be minus that, right? Nice thing about cosine 60 is going to be 0.5. Sure. Oh, x in feet. Sorry about that. X. Carry my, and I forgot to put the prime there. Okay, tricky thing there. And then the next one I need to get to is c. X will be what? Oh, that's one dimension I didn't put up there, is it?
X is going to be
4. Where's my pen? Okay, so x is 4 feet. What about y? For sine 60. And then z, minus 4 cosine 60, or minus 2. Okay, we comfortable with that? Okay, so that's what I need in terms of setting up my equations. So the next thing we dive into is our equilibrium equations. And we've got now a free body diagram which identifies all of my known and unknown forces. Now, since I'm doing scalar equations here, I'm not doing scalar equations. I'm going to be using cross products. I don't necessarily need to show a positive or negative direction here because the cross product will take care of it for me. So that's what I'm going to do then, is I'm going to take my moment equation and I have to include all of the forces because I'm taking all of these forces, moving them out of their lines of action and moving it here to create a couple. So I've got my 40, I got my 2 components of B here, I got my 1 component of C here. And then you choose your poison. I like setting it up in terms of determinants. It's a little easier to see, but we'll set up so my first one is over to those B components. So my R vector is, again, just 5 in the x direction, positive 5. And again, keep this order. I noticed a number of you had some difficulties on the last exam there in terms of which one. It's going to be unit, position, force. Has to be that way. And then the BZ and the BY I've got shown as a positive, and the BZ I have shown as negative. So I'm going to show it, I'm going to put it even as an unknown as a negative there because I'm showing it in that direction there. If the sign wants to correct me, it'll come out as a negative value there. Okay, that's the first component. Then I look at my C component. It's got a few more things in the position vector there because I've moved over 4, and then I've gone up a little bit, and I've gone over in the z direction there, or negative z direction there. But the nice thing is then when I look at my component of my force there, knowing the fact that that's a smooth bar there, I'm going to have only force in that perpendicular direction there. So I have lots of zeros again in my determinant. And then finally my weight. And again, I know my weight's acting in that negative direction there. And I put in my R vector as shown. So that's my moment equation. And then what I'm going to do with that is set that equal to 0, which means then I'm going to drive that x component, the y component, and the z component equal to 0. So we'll go through and let's put together all of the things under I. So in terms of I, I'm going to hit a 0 that way and a 0 that way. So there's no contribution from the the RB portion there. If I go this way, I'm going to pick up a 3.464 in the CZ. If I go the other direction, a -2 and a 0. And then I look at the next piece there, and I go this way, and I end up picking up a 0 that way, this way. But when I go this direction here, I'm going to have a 1 and a -1 and a -40. But it's also in the minus direction, right? It's going the other direction there. So I'm going to have lots of minuses here. And this is always the thing that catches you a lot of times with these determinants. You've got to make sure you keep all those signs in there. And that's everything in the I direction there. We'll look at our j direction. Walk through those. J hits a 0 going this way. This way, I'm going to be able to pick up the 5 and the minus BZ. So I got a -5 and a minus BZ. Go to the next one here. Pick up a 0 that direction. I go this one, and I'll be picking up a 4 in the CZ. It's already in the minus direction there, so it's 4. The CZ is positive. Oh, not finished yet. Then I go look at my last one, and it hits a 0 this way. I go this way, it hits a 0 there, so I actually am finished. And then the last piece will be my k component. And k will pick up a 5 and a by. Go in this direction, it picks up zeros. K going this way would be 4 and 0 that way. 3.4 and 0 that way. Go to my next piece there. I'll pick up a 2 and a -40. And then a 1.7 and a 0 there. So it's already in the minus direction there. Is it? No, that was a positive direction. That's a positive direction. 2 and a -40. And what I've done now is assembled my scalar equations. These are all the pieces then that have to go to 0. Sure.
Where did the minus sign come from on the second part of J?
This one here?
Yeah.
Let's see, which one is it? This way. So my J, remember it's positive if I go this direction, negative if I go this direction. Or if you do the minors, that, you know, if we do this one, it's positive minus positive. So, but if you're going that direction, it's minus. I always remembered in terms of the 3 by 3. But
And when you did the -5, was that because you're trying to incorporate that it's the negative position for each one?
this one here?
Or the J portion is the I is positive?
Yeah, actually, I should put it out like so.
Yeah.
Because it was a positive 5. Yeah, that's a better way of putting it. Yeah, because my 5's this, and then it's a minus BZ, but it's the minus direction because I'm going, you know, it's positive this way and then minus.
So alternating.
Yeah. So that's a better way of putting it. I like that idea.
But then isn't the 4CZ also minus? So you should multiply the minus sign by that as well?
Yeah, it's 4 CZ.
Okay.
So I've got the minus outside and then the 2 positive quantities. Yeah, okay. No, good. I like that. It's much cleaner.
In 2D, we were able to do the cross product method that we're doing right now, but we were also able to do the perpendicular distance method. I was wondering if we could still do that with the components of the moment. And then
Yes, you can. And as a matter of fact, the really good point is when you look at these things, that's what these are.
because like the AZ and the So you can just find relationships like that, and you also know it's not moving in
Sure.
Y. So
Well, that's a good question. While we're there, let's look at that. Okay, so we're taking moments at A here. Okay, let's think about rotation about the x-axis here. Okay, when I think about that, BZ is not going to. So x-axis will be up here, right?
yeah.
So this will be all my x-axis components for a moment about A. Okay, so it's actually along the x-axis because A is along the x-axis there. So BZ will not participate. I don't see any BZ or BY in there, right? Because it's on the x-axis. That's not going to contribute. My 40, well, let's think about that. If it's going to twist, then it's got to be that perpendicular distance along that z direction there. Where am I? Yeah, the 40 here. So it's -1 over, and then the 40 pounds down. Okay, now let's think about sine. Minus, minus, minus. So we got line minus. Well, yeah, here's my x direction. It's twisting in the minus direction.
Yeah, it's just a lot shorter of a process than doing all the cross product stuff. If you can
Oh, sure, sure. If you're comfortable doing it that way. And the key thing is you get that out of the cross product. But if you're comfortable doing it that way, yeah.
Yeah, and then another concern I had though was because I was thinking, would A, Z, and BZ be equal because the board is leaning on the right side against the pole, so I don't know if those forces would be equal or not.
Well, we'll solve that, but think about it. If everything was symmetric, I would agree with you. But the problem is we've got this guy over here.
And
Yeah.
not exactly the same distance from the center of mass or whatever.
Yeah.
One's 2, one's 1.
Oh, yeah, that's right. This one's 1 and this is 2. So, yeah, when we get into trusses and that sort of thing, one of the rules of thumb in terms of thinking about symmetry is it has to be a symmetric structure and a symmetric loading. So you got to look at both pieces before you can assume a symmetry or a BZ equal to AZ and that sort of thing.
So this would give us a reaction to A. We have to do it again 2 more times for B and for C.
No. What we're going to say, what we're doing is we're establishing some equations, but look at these equations that we have here. I've got an equation with one unknown. I can solve for ZZ. Oh, once I've done that, I can plug that into here, get this piece, and that's where we're going. This is only a BY. So I'm already solving 3 of my 1, 2, 3, 4, 5 unknowns. So what we're doing what we'll find is when we do that, and it brings up a good point, oftentimes the first thing we usually want to do is a moment equation. And we want to take a moment equation where we can eliminate some of those unknowns. Once we do that, though, what we'll find is then we can maybe just do sum of forces for the next couple of equations. So let's finish up the problem. You're a little ahead of me there, but so CZ is going to be equal to, oh, you guys are so far ahead of me. 11.55. That's pounds, right? Okay, and then we're going to plug that into J.
So you're just doing the sum of the forces in each direction basically right now?
What I'm going to do is, to drive any sort of vector equal to 0, each of these, this is the x components, this is the y components.
Each one equal to 0. And then
Each,
solve for that.
exactly. That's my 3 scalar equations now. My first 3 scalar equations there. So BZ over 5CZ. What'd you get?
46.19.
No, I got 9.238. 4/5 of 11. Well, good thing you're doing it here and not on the exam. Think of it that way. We're going to get it out of the way early. Make those mistakes early. Then finally, we've got our last piece there, or our last equation in that moment equation. By is equal to what? Over 5. Where'd you go? 16. Okay. So with our moment equation, we've already gotten rid of 3 things. Now, that may not always be the case. We might end up with situations where we might have simultaneous equations to solve. You know how to do those, do substitution and that sort of thing. Okay, so now getting back to the young gentleman's point there, do I need to do a moment from now? Well, no. All I'm missing is AX and AY, right?
AZ. So that's just CZ, BZ.
So what we can do at this point in time is just do sum of forces in the Z direction. And since I do know that direction, so let's go back to thinking about our situation there as BZ and AZ equal to, well, we haven't solved. Oh yeah, we got BZ. So we got BZ at 9.2, and then the AZ is 2. And that's because of the unsymmetric set of supports that we have there. But again, be careful, make sure that when you're doing this sum of forces that you pick up all of the pieces. And then the final piece is sum of forces in the y direction. And then we solve for AY is 24 pounds. So even the supports in terms of AY and BY are not going to be the same. Yeah, 16, 30, 40 would equal 40. And the only actual vertical force is the 40.
40 for BY in your equation with your little half part.
Okay, right.
This one?
Oh,
Oh, the other.
Some of the forces in the line.
Down one.
Oh. Oops.
Like in that, everyone caught it.
That one, yes. Okay, good eyes. Okay, so the key thing is note then, we want to try to use the force equations if we can. They're a lot easier. We're not multiplying things times each other and making sure that we've got moments. And oftentimes things might have inches and feet and stuff like that where you've got to make sure everything's going to be the same. So if we can do it with one equation, get a bunch of them out of the way, then take a look at your force equations and see if you can solve it. So I didn't have to do I could do moment equations if I was, you really want to. I'm not going to stop you from doing it. But it's generally easier, especially when it comes to exams, to get yourself down to force equations when you can.
I was just going to say, would you leave it like this, like on a test, or would you have to turn it into the total moment, or the total magnitude of B and direction of B, or could you just leave it in components?
I usually tell you what I wanted. I'll say I want it in components or give me the resultant. So again, when it comes to exams and quizzes, read the problem.
Because this one just says determine the reactions. So if you
Yeah,
just leave it like that.
I would leave it like that in this particular case because it,
That's a lot less work.
yeah.
Are the pound signs just marking your answers, or does it mean something?
What?
The pound sign?
Hashtag units.
Oh, yeah, hashtag pound. Everybody, I'm sorry, that's shorthand for pounds.
It's
And
actually called a pound. It's not called a hashtag.
yeah. Oh, is it? Okay, I haven't kept up with all the.
No, it really is. Everyone's like hashtag. It's actually called a pound.
I can go to pounds if you want. I'll put pounds there. Jeez, you guys are tough.
Just a product of your generation. All you need
Yeah.
You're saying that.
Well, we had to write everything. We.
Engineer shorthand from not being able to read LB.
No, because everyone's like saying it's hashtag and they're all confused. So like,
Yeah,
hashtag, I don't see
The
Twitter.
pounds.
Yeah.
Should be LB.
That's when a little bird flies in and twitters away. Question?
Are we assuming that the x's are equal to 0?
Yes. Now that's a good point. We talked about that earlier there. When we think about it, that it's really unstable because I don't necessarily have, unless I said that these were frictional, they had friction or anything like that, I really don't have anything to resist in x direction. But notice the only force I have is a vertical force, and then this support force is perpendicular to that in the z direction there. So yes, x is automatically equal to 0 in this particular load situation. The problem is, and again, this is what I want you to think about in terms of being designers, is that if any sort of force shows up in that direction there, you got a problem with your sheet of plywood there. It's going to be flying off somewhere. Okay, so we'll dive into yet another problem, or at least get started on it. I'll let you read it while I do some erasing here. Okay, so we've got the situation that we're pretty familiar with now in terms of especially 3D forces. We've got a bunch of cables that we've been given the endpoints. So we're going to end up doing a lot of unit vectors, basically, because we're going to have to get those force vectors from BE and BF into some sort of a unit force. And then it'll be an Fx component that we'll solve for, an Fy component, and an Fz component. We've got cable D there that I think has load on it. Oh no, I guess, yeah, tension in the cable is 14 kilonewtons. It's parallel to the, what's parallel to the x-axis? It doesn't look parallel to the
Parallel
x-axis.
to the x-axis.
I think it's supposed to mean that
It doesn't look parallel.
all.
Equals 0. And the externity is going down.
Oh, okay, yeah. See, the picture doesn't, yeah, because theta, our little theta is basically equal to 0 there. So it's basically going along the x-axis there. Oh, that's a lot simpler problem than I thought. Piece of cake.
If you can even read the drawing.
Yeah. So this is where we go. Now we need to start thinking about, okay, the first thing we do is create a free body diagram. This one's a little easier because the free body's pretty straightforward. It's going to be a stick.
This is the x direction. There's no point in having that equal there. For no apparent reason. Yeah. Because the phi is equal to 0. Yeah. So not. They just put that there for like in case they want to change phi.
Got it? Okay. Okay, so what we're going to do, I'm going to start off early and put what I think is going to be my coordinate axes. And okay, so then I need to start thinking about, okay, what's my known force is going to be parallel to the x-axis there, although it's acting in the negative sense. And then the other two things I need to think about is, okay, I'm going to have a set of forces here from these cables, but the only thing I have to identify them is going to be a set of distances here. One will be here, and one will be here. Oops.
Let they go not to the top, but just short.
Oh, right. reading my picture.
Put it in.
Yeah, I can make it higher, couldn't I?
But then you get rid of that tension.
You guys are such artists. Why did I hire a bunch of artists here? I tell you. Okay. There, are we happy? There's our point B. Point C is up here, and that has our force now. TCD. And then the other thing I haven't done is then I've removed the ground from A. And we know it's a ball and socket, so how many unknowns do I have there? Yeah. It's just going to prevent me from going. So I'll substitute the ground then, or what the ground on that ball and socket joint is providing is just going to provide me the 3 sets of forces, but it's going to allow me to rotate. And then I need to start putting in dimensions here with a pen that actually writes. And this is in meters. So to point B is 8 meters, and it doesn't look particularly proportional, but 7.5 meters. Which covers actually both of them because they're along the same line there. Okay, so ugly drawing. But again, a couple of things. We were talking about symmetry earlier there. We are going to take advantage of symmetry here in this case because we know that these 2 cables are actually rather symmetric there. They're symmetric about the x-axis, right? They're both 6 off, and they're both 7.5 down the x-axis there. So we're going to take advantage of that. So I need to determine my unit vectors. We'll start off with BE. So again, in terms of the x direction there, I'm starting off at 7.5 away from me. By the time I get to the mass there is going to be at the origin of the system there, so it'll be equal to 0. J, I'm starting off at the ground or at 0, and I'm coming up 8 because my positive y convention is that direction. And then the K, again, it's 6 over. And I'm going to bring it back to the origin again, so it'll be equal to 0. And that's all in meters. Again, to go to unit vector, I'm going to have to then do my Pythagorean theorem there and get the length of that cable. I do like the author because he likes to come out with these really nice numbers there. So it comes out the total length of that cable is 12.5. Then my unit vector is just simply going to be the vector BE over the length. And then creating my unit vector, I just simply divide all of those numbers by 12.5. And then taking advantage of my symmetry, I know that basically everything's the same except for the z direction there. It's just simply shifted over on the other side there. So instead of a 0.48 in the positive sense, it'll be a minus 0.48. So again, a little time saver there. Take advantage of that symmetry. Now, again, in terms of taking an equilibrium equation, what we'd like to do then is take it where we've got the most unknowns. We've got 3 at A, and I've only got 2 up there at B. So we could do it either way, but I'd just as soon take it at where I can eliminate most of them and get those 2 out of the way. So that's my 3 pieces there, and fortunately, actually, one of them's basically going to be the same. RA to B is going to cover both the tension of BE and the tension of BF. Make this a little. Now the interesting thing, that's my first piece there. But notice the only unknown in that whole thing is BE. We're talking BE, but we're multiplying it times that unit vector. So we're looking at the various proportions of it going off in the x, y, z direction there, but it's still one unknown in that equation there. Similar equation for BF. This time I'll make sure I have enough room. But my position vector I didn't talk about, but it's pretty straightforward. It's just simply 8 feet up in the y direction there from A to B. And then this will be the similar hold it. I'm this. Yeah, that's what I'm sitting there thinking. Hold it, I'm missing my minus signs there, aren't I? So I should have a minus sign on each of these guys here. And then my final piece there is that tension in cable, CD. and we set it up like that, basically it's going to be, now it's at point C, so it's going to be 8 plus the 4, or 12 feet up. And then it's acting in the minus x direction there. And then what we want to do is simply put our components together there. So we'll look at everything that's going on in the x direction there. And we've got an 8 and a 0.48 in our positive sense. So we got an 8, 0.48 TBE. And then nothing going in the wrong that direction there. Same thing with that one, except now we've got a minus sign on it. Oh, except that's BF. And then looking at our final piece there, we hit a 0 that way, we hit a 0 that way, so there's no contribution there. Let's consider J. So this one, nothing, 2 zeros on either end there. Same with this one, same with this one. That's a real easy one. And then finally, our K component. Go this way, we pick up a 0. But this way, we're going to pick up an 8. But it's in the minus sense. Same thing with this one then. We're going to pick up the 8 and the TBEF, and it'll be minus. And then finally, our last piece here, we'll pick up a 12 and the minus 14. Now, the reason I wanted to go this far is, does this make any sense to you? Why would there not be any sort of moment in the y direction? It's that special case of equilibrium. Remember, all the forces going to a line? All of these forces basically go to this line here. So there's no resistance. None of those forces can provide me any sort of resistance of a twist about that y-axis. So it does make sense. I'll post the solution then for you tonight so you can take a look at it.